Welcome back to the Foundry by Forge College. I'm absolutely thrilled you're here for this explainer. If you've been following along with our blockchain fundamentals track, specifically the Introduction to Blockchain Technology module, you'll know we're right in the middle of exploring blockchain in action. And hey, if you joined us for the last lesson, Synthesis of Blockchain Basics, you know we spent, well, a lot of time digging into the theoretical foundation of how networks actually agree on a shared history. Block ordering, consensus rules, the whole shebang. But Today, we are stepping out of the theory manual and walking straight into the drafting room. We're going to look at real-world blueprints. We're taking those abstract concepts like hashes and consensus and asking, okay, where do these properties actually matter in the real world? How do we literally build with them? Okay, let's dive into this. Here is our blueprint legend for the day, so you know exactly what we're going to build. First up, the blockchain toolkit. Second, comparing finality styles. Third, blueprint 1, which is document notarization. Fourth, Blueprint 2, tackling the supply chain. And finally, number 5, the engineer's final checklist. All right, section 1, the blockchain toolkit, reviewing our primitives. Before we start building, we absolutely have to review our core engineering tools. Because look, before we write a single line of code, we have to know our tools, our primitives. And our absolute foundational tool here is immutability. You can think of this kind of like a physical tamper-evident seal on a glass jar. In the digital realm, we use cryptographic chaining to get this effect. Each block's hash is uniquely tied to the data inside it and the block that came right before it. So if an attacker tries to sneak in and alter a previous block, the hash changes, and boom, every subsequent link in the chain shatters. There's just no way to rewrite history without everyone noticing the broken seal. Now, alongside immutability, our toolkit has a few other essential mechanisms. We've got transaction finality, which determines exactly when an action is permanently settled. Then there's peer-to-peer networking, acting like this giant, decentralized megaphone system for discovery without needing some central server. We also have data transparency, basically turning our systems into glass boxes where anyone can audit what's inside. And we can't forget read and write models, which dictates exactly who gets to hold the pen to write history and who actually has the clearance to read it. Oh, and of course, scalability considerations. That dictates how large our factory can grow before the machinery, starts to slow down. Moving right along to section 2, drafting finality. When is it really settled? Now, what's really interesting about this is how we handle confirmation depth in a decentralized network. Let's look at probabilistic finality first. It's kind of like slowly drawing concrete. The more blocks that pile up after your transaction, the thicker that concrete gets, and the higher your confidence that the transaction is truly irreversible. You might accept wet concrete for, say, buying a coffee, but if you're transferring millions of dollars, you're definitely going to wait for it to cure completely. Immediate finality, on the other hand, is literally like snapping a Lego brick into place. Once consensus is reached, it is final. Instantly. The trade-off, though, is that you have to trust the voting parties much more heavily for that instant snap. Okay, let's pull out our first blueprint. Section 3, Blueprint 1, Document Notarization, the read-write model. So imagine a government office that's trying to issue tamper-proof ownership licenses for something mildly absurd. Let's go with a pet rock. They need an ironclad record. Approach A is the on-chain write. That means putting the full license right on a public ledger. Immutability enforces the tamper evidence, sure, but public read access completely exposes sensitive personal data. And honestly, storing thousands of pet rock pictures on-chain is super expensive. So developers usually pivot to approach B, the off-chain anchor. Here, they submit only a tiny cryptographic fingerprint, a SHA-256 hash, to the blockchain and keep the full document off-chain in a private database. It's a brilliant workaround. It preserves absolute privacy and low costs while still borrowing the blockchain's incredible immutability. Let's turn to our next massive blueprint. Section 4, Blueprint 2, Supply Chain Traceability Workflow. And by the way, studying these kinds of complex workflows is a total staple in Forge College courses. Let's trace a batch of artisanal glow-in-the-dark sneakers through this workflow. Let's move through the steps and see how this builds. In step 1, the factory creates an event record stating these awesome sneakers exist. But to protect their trade secrets, they use an off-chain hash anchor. In step 2, the transport company uses a permissioned write to update the custody log, meaning only authorized shippers can actually append this transit data. Step 3, a quality inspector approves a feature, relying on transparency and finality rules to determine exactly when that inspection is considered permanently valid. Step 4 brings us to the retail level, where read models allow consumers to query the ledger and verify provenance. Like, did these actually come from the artisanal factory?
Finally, step 5 is where scalability really kicks in, using off-chain reconciliation and indices for lightning-fast queries without totally bogging down the main network.
Which brings us to Section 5, the final inspection, the engineer's checklist. Let's pack up these blueprints and summarize. So the crucial point is that these blockchain concepts aren't just abstract ideas, they are highly functional operational levers that dictate performance. Going forward, I want you to carry this 3-step checklist into literally every Web3 project you evaluate. Number 1, identify the exact guarantee the application actually needs. Number 2, map that need to a concrete implementation pattern. So is it an on-chain write, an off-chain anchor, a permission setup? And number 3, be fiercely honest about your operational trade-offs regarding latency, cost, auditability, and privacy. Internalizing this checklist perfectly prepares you for our upcoming lesson on financial and payments use cases. Ultimately, the technical decisions you make using these tools don't just change the code. They shape the very architecture of trust in your entire system. So the next time you interact with any digital record, I want you to ask yourself, whose ledger is this actually written on, and how much wet concrete is holding it in place? Keep exploring and building, folks. If you want to keep expanding your toolkit and diving deeper into the mechanics of Web3, definitely head over to forge.college. Thanks for joining me for this explainer, and I'll see you in the next one.